Okay. I just wanted to take a second and go back over the notes from today because I think the lecture was a little jumbled, and so I think it could be good just to go over everything again. So this is just an introduction of us. Um, the ScioVirtual stuff I think you've heard in a few. There's the Google Classroom code, so make sure to join that. And as far as expectations for the class go, download LT Spice, or we'll talk about some other alternatives for circuit simulation next time on Wednesday. But if you can download LT Spice, that would be best because it's lightweight and it's really easy to use. So then ask questions, do the optional daily problems, and ask questions, 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 ask questions. We can't emphasize this enough. We really want you guys to ask questions. On Monday, that was really great. There were a lot of questions happening. That's what we love to see. But I don't want that to kind of die away. I want to make sure we're always asking questions because if you're confused, someone else is also confused, right? So be the savior and ask the question. So, what is electricity? So, electricity is, at a high level, energy caused by the existence of charged particles, okay? So, opposite charges attract, like charges repel. We're hopefully all familiar with that idea, right? Two positive charges close together are going to push away from each other. Positive and negative close together are going to attract each other, right? So Coulomb's law describes that process. And this is Coulomb's already here. F equals K, Q1, Q2 over R squared. So K is a constant. It's about 9 times 10 to the ninth. Q1 and Q2 are the values of the charges. So the charge magnitude is measured in coulombs. We measure height in meters. We measure the magnitude of charge in coulombs. And the distance between the charges is R. So you can see as the charges get close together, that denominator, that R squared, gets smaller, as the whole number will get bigger, right? And as R squared gets bigger, the whole number, that F, the force between them, gets smaller. So for two particles that are very far apart, there is not much force between them. For two particles that are very close together, there's a lot of force between them, okay? Now, typically, we use electric fields to describe where a positive charge would be moved in the presence of other charges. Um, really, the idea of fields is it's a really helpful way to describe certain things in physics. Um, the actual math of like what fields are and how they allow us to do things is a little above the level of this class. But for our purposes, an electric field describes where a positive charge moves in the presence of other charges. And so notice it's where a positive charge would be moved, okay? So we draw electric field lines going away from positive charges then into negative charges, right? And again, the goal is just to describe where a positive charge goes, okay? Field lines point away from positive charges. So as a quick check, where would a charge of magnitude plus q go if it was placed in the middle? The answer to that is, of course, towards the negative 8q charge, as attracted to the negative charge and away from the positive charge. And what about a charge of minus q in the middle? Well, it would go towards the positive 4q charge, towards the left, because it's attracted to the positive charge and pushed away from the negative charge. And if we were to draw the electric field lines point away from a positive charge and towards the negative charge. Now, what's interesting is figuring out exactly the directions that these lines point is not easy. And the math gets actually quite difficult, which is why these curves look kind of strange. I mean, like, why does this one loop around like that? Why doesn't it just go directly towards the negative charge? But um, if you can kind of assume the math works as the math works, we can just look at this diagram and see, yes, the electric field lines do indeed point away from the positive charge and towards the negative charge. And if I had a positive charge, it would move in the direction of the electric field line. It would move towards the negative charge and away from the positive charge. So when we talk about electric fields and fields in general, it's convenient to think about things such as potential and potential energy. If you ever pushed a spring, you know that as you compress the spring, you feel like it's pushing back, right? That spring is storing energy, storing elastic potential energy in that case. So you push it in, and then when the spring extends, it pushes my hand away, right? Now the spring is no longer compressed, it's no longer storing that energy, but my hand is moving. My hand has that kinetic energy. What the spring has done is it's done work. That's how we define potential energy, the potential to do work. Doing work is just changing energy from one form to another. Okay. In the case of springs, we're changing that energy from the compression, the elastic potential energy of the spring, into movement of whatever gets sprung away from the spring. In the case of gravity, we're changing gravitational potential energy, like a ball on top of a skyscraper, to kinetic energy when the ball falls off the skyscraper, and as it falls, it gains speed until it hits the ground. And in the case of electricity, when you have two charges really close to each other, that's a high potential energy configuration. And as they move far apart from each other, or as I guess in the case of positive charges in particular, as those two positive charges are pushed away from each other, they lose that potential energy and it's turned into motion of energy. Okay. So that's what I'm saying. As a positively charged particle moves along the direction of an electric field line, its potential energy decreases. Okay. Now, this should make sense, first of all, right? If I have a positively charged particle on this line right here, and it moves along the direction, it's initially really close to that positive charge, it's being pushed away really strongly, and then as it moves away from that positive charge, as it gets pushed away, that pushing, that potential energy is becoming kinetic energy, the energy of motion. However, as a negative charge moves along the direction of this electric field line, it's moving towards something that'll push it away, right? So actually, its potential energy will increase as it moves along the electric field line. And if we take a moment to think about what that actually means, that means our description of where a particle might go, of how much potential energy a particle has, is dependent on the charge of that particle, which can be useful in some cases. For example, if I wanted to say, suppose you have two particles right here, and then eventually one particle's all the way over there. How fast is that particle moving? Then yes, you want to be able to describe the potential energy. But in circuits, we don't really talk about individual particles so much. We want to talk about the properties of space, the properties within the circuit itself. That's why we talk about potential instead of potential energy, okay? So this formula right here, UE equals KQ1 Q2 over R, that's the formula for potential energy. And you'll notice it's dependent on both the charges, right? But say I just have some charges spread out through space, and I want to determine if I were to put a charge there, what would its potential energy be? I describe that configuration of charges with with the potential, okay? The potential is the property of the environment or the field, whereas potential energy is a property of the environment and a charge in that environment, okay? Potential is, strictly speaking, the potential energy per unit charge. And that's why we really talk about potential in circuits. We're not talking about specific charges themselves, we're just talking about charge in general, right? And that's what we want to talk about, the potential energy per unit charge. So this will become a lot more clear once we get to a simulation and a demo in a second, but just as a quick check, a positive charge sitting near this positive charge right here would have a very high potential energy, okay? But a negative charge at the same location would have a low potential energy, right? Just based on this formula right here. Just forgetting even just thinking about it, just for looking at just the formula, it would have a low potential energy for a negative charge right there. But what about potential? Well, the potential of those two would be the exact same. The positive and negative charge have the same potential because in reality, they don't have a potential. It's the field that has the potential and they're just being plopped in there, right? But the difference is a positive charge will move along the electric field line from high potential to low potential, whereas a negative charge will flow along the opposite of the electric field line from low potential to high potential. Okay? Positive charges move from high to low potential. If you're kind of completely lost about everything, this is the one point that you need to remember. Positive charges move from high to low potential. Okay? So this is just a FET demo, which I think is really helps really solidify these concepts. So first of all, we have a positive charge right here, just a single positive charge nailed to the table. Far away from the charge, I have low potential. As I get closer to the charge, my potential increases. You see that? Now, what if I put just a negative charge in there? I put a negative charge here. Far from the charge, I have a negative potential. As I get closer, it gets even more negative until it's a super, super, super duper negative. So it is lowering, it's just getting more and more negative now in this case, okay? Now, if I put a positive and a negative charge here, okay, this is that dipole configuration, the one that we saw in this slide right here. If I do this, in between them, the potential is about zero, okay? As I get closer to the positive charge, the potential increases, and as I get closer to the negative charge, the potential decreases, okay? And what does that mean? Well, what that's saying is the electric field lines point from high potential to low potential, okay? A positive charge in this field flows along the direction of the electric field lines, and along the direction of the electric field lines, the potential decreases. So, positive electric charges move from high potential to low potential, okay? And this demo is really fun to look at. You can just Google fat charges and fields 1.0.65 and you can play with it yourself. I strongly encourage that. So where do electric field lines point relative to positive and negative charges? They point away from positive charges and they point into negative charges. Okay? Where does a positive charge go in an electric field? It goes along the direction of the field line, whereas a negative charge goes in the opposite direction of the field line. And what does the potential difference between 2 points in space tell us? It tells us whether a positive charge is likely to tend from one location to the next, okay? What I mean by that is if I have 10 volts right here and 0 volts right here, a positive charge will go from here to here, from the 10 volts to the 0 volt place, instead of from the 0 volt to the 10 volt place, because positive charges go from high potential to low potential. And for this reason, you heard me just use the term volts, but for this reason, we use the terms potential and voltage synonymously. Voltage is that force that kind of drives current, right? And potential is what going from high to low potential is what a positive electric charge wants to do. And so we really do talk about potential and voltage synonymously. They're the same thing. And that the unit for potential is volts. And as we'll see in the next one where we talk about circuits, voltage is what moves charges in circuits. So please let me know if you have any questions about this. This is the more physicsy lecture than the future content will be. It'll be a lot more circuits moving forward. But understanding what potential is quite important. So thank you.